Okay, welcome to the today's class. We discuss about nMOS fabrication. So far we have seen, let us recapitulate. Recap. So in the previously that we have seen that the construction of the MOS transistor, construction of or the theory of the MOS transistor, right? So theory behind MOS structure, okay? The second one that we have seen that the qualitative analysis, the last class, analysis of MOSFET. So MOSFET that we have seen, that means that what is the operation of the MOS transistor, when it is on, when it is off, when it is on, what is the condition has to holds good, when it is whether it is in linear, what kind of condition has to be holds good, when it is on, when it is in saturation, what kind of equation or what kind of condition has to holds good. All these things we have seen in the qualitative analysis. Now today we are going to look at the physical. Now the physical structure of MOS transistor. Okay, so this is what we are going to see this one. So the physical structure is based on layers, So what are the physical layers that we have to use to construct the MOS transistor? We look at in this particular class. So this is normally known as in technically we can call it as fabrication. We can call it as fabrication or making steps, making. So anything we can call it as, but actually people will normally call it as fabrication. Okay, so so whenever we have seen that the physical construction of the MOS transistor. So what exactly how it look like? For example, you consider this. Okay, copy. So as everybody knows that this is what the theory that or the construction that we have seen in the previous class. Okay, so what we can see that here what we have to form, first one is a bulk. Okay, so bulk or body, we can call it as bulk or body, or sometimes we can call it as substrate also. Normally we can call it as a substrate only. That is the thing that we have to create. Okay, so the next one is oxide. Okay, it is a gate oxide that we have to create. Metal we have to create, and diffusions that we have to create. Diffusions, so that means source and drains are nothing but diffusions only. Okay, so finally we have to go for metal contacts. Okay, these are metal contacts. Okay, this is also a metal contacts. So already here is the gate is available as a metal, so no need to consider it as a metal contact required for this one. Okay, small terminal is sufficient for that one. Okay, so of course significantly we use the same structure for that one. Metal also we use for the gate. Okay, so therefore this is what we have to fabricate or manufacture. Okay, so in order to do this one, what are the steps are there? Okay, so we have to consider the fabrication steps. What are the fabrication steps involved in this one? Okay, so I can say that here I will tell you one particular slides show here in this way. Okay, so in order to fabricate the transistor here, these are the steps that we have to follow. As you can see here, so what are the steps? First one is a crystal growth. The second one is field oxidation. The third one is photolithography. The fourth one is gate oxide. Fifth one is gate formation, source and drain realization, metallization. So essentially three steps that are involved in this one. Just a second. Excuse me. Okay, so essentially there are 7 steps are there, right? 7 steps essentially we have to follow. Okay, so what do you mean by the crystal growth? First of all, okay, so the crystal growth means formation of suitable substrate. Okay, so what is the first step that we have to consider? The formation of suitable substrate. Or I can say that, as I mentioned, that whenever the moment, if I'm talking about the substrate, you can also assume that this is the body, or you can say that this is a bulk also. So any name can be suitable for that one. Okay, so first of all, whenever you want to fabricate something, first we have to create a suitable substrate. Okay, so for example, if you consider an nMOS transistor, for example, an nMOS transistor, P substrate is required. Okay, P substrate is required. So that is called suitable substrate. Okay, so in order to create a suitable substrate, okay, we have to follow the process called, or a fabrication step is called crystal growth. What we can call it as crystal growth. Okay, therefore the crystal growth is a process by which we can create a suitable substrate. As simple as that. Okay, so what is the steps that are involved in crystal growth technique? Okay, so generally silicon is in the powdered form in nature. Okay, it is in powdered form. Okay, we have a powdered form that is available. Silicon atoms, silicon is present in the powdered form. It's a sand actually. Okay, so what we have to do, we have to convert this powdered form into a crystallized structure. We have to form a crystallized structure. Okay, and a solid material, that means a single crystal silicon that we have to create. So that means we have to the solid material that we have to create from that one. Okay, so this particular element we can call it as ingot. So therefore this is what actually this is the one type of polycrystalline silicon. This is solid silicon. This is normally it is a powdered form that is available. From the crystal growth technique, we can form solid silicon, something like this. This is the one solid silicon, second, third, fourth. So different diameters. So different diameters silicon, single crystal silicons we can create, something like this. So these are the different diameters. So this is a large diameter, small diameter, something like this we can create here. Okay, so therefore I will show you that video also after some time, then you can understand how do we make this kind of thing. Okay, so whenever we have a solid crystal, whenever we have a powdered silicon is there, that we have to melt by using the temperature. Okay, so therefore we have a solid silicon, place it in the one particular vessel and use the temperature. By using the temperature, this powdered silicon will be melted, and after that one it will be converted into solid material. Right, so therefore this powdered silicon is converted into solid. We have to melt this powdered silicon into liquid form. Okay, we have to melt this one. So about 100 degrees centigrade we can, 1000 degrees centigrade we can melt this one. Okay, so therefore if you melt this one, and if you by providing some air, it is automatically solidified. Okay, therefore the solidified single crystal silicon we can call it as ingot. Ingot. So therefore solid state single crystal silicon is called ingot. Okay, so that is the first step that we have to do. Okay, so single crystal silicon we have to create by using the polycrystalline silicon. Okay, so now what we have to do, we have to cut this into different pieces. So we have to cut this ingot into different pieces, right? These are different pieces. So one particular piece is called this one. Okay, so this is a one particular piece having some thickness for this one is also available. So this is another chip. This is another the wafer. Normally these are called this small piece of thing we can call it as a wafer. What we can call it as wafer. So this entire solid material we can call it as ingot. Okay, a small piece of thickness small thickness material we can call it as a wafer. We have to cut into different pieces. One piece we can call it as wafer. Okay, different diameters of the wafers are available here. So this is one diameter, this is some other diameter, this is some other diameter. So therefore, depending upon the ingot diameter, we can have a different wafers are available. Okay, so that is a very, very important for us. Okay, that will be acting as the body or a substrate or it's a bulk, right? So therefore, what we should understand about the crystal growth, it is the technique by which we can convert the powdered silicon into crystallized silicon in order to make a suitable substrate. Clear? The crystal growth technique is the process by which we can convert the powdered silicon into single crystal silicon in order to form a suitable substrate for the device fabrication. Right? So that is the first step. Next one is, okay, now we have a wafer here in our hand. Wafer is available here. So in the wafer, so some part of the wafer is used for the formation of our circuits. Okay, this is the one circuit, this is another circuit. It can be a same circuit, it can be a different circuit, it doesn't matter. So therefore, we have to create by using the different ICs. So these are called the small square boxes. We can call it as a IC actually. This is called a chip. So this is what actually where our circuit will reside. Okay, so therefore this is one of the chip that we can consider as. This is also called as chip or die or integrated circuit. Any name we can call it as. Okay, generally we normally call it as a chip. Okay, so what is the inside of this chip? So this is what entire circuitry is there. So what is the inside of this one? This is the entire circuit. Entire circuit is available in it. Okay, so therefore this is what the circuit actually I have shown here. Some microprocessor I have shown here. So so this is a graphics card actually that consisting of millions of transistors in it, and that will be covered with the top, something like that. So one of the important essential requirement for the wafer is that the wafer size can be anything. Okay, so from 75 millimeter to 155 millimeter. So typical diameters. What is the typical values generally used for the wafer is this much. And of course, the thickness of this wafer is also 0.4 millimeter thickness. Normally, people will use. And the second, so diameter of this is the one thing that we should notice that, and thickness we should notice that, and impurity concentration is the third point that we have to remember for the wafer. Okay, the impurity concentration will become 10 to the power of 15 per centimeter cube. Okay, so this is actually the centimeter cube to 10 to the power of 16 centimeter cube. Okay, so therefore this impurity concentration will decide the resistivity of the material. Okay, that resistivity can be 25 ohms to 2 ohms per centimeter, 2 ohm centimeter. So generally it is actually 2 ohm centimeter. So therefore, whenever you are fabricating, whenever you are using, whenever you are taking the suitable substrate, sometimes it is necessary to consider that what is the thickness of the wafer that you are considering. Okay, what is the diameter of the wafer that you are considering, what is the impurity concentration and the resistivity we have to know. So actually the diameter of the wafer is not that much important to fabricate a transistor actually, but the thickness of the wafer is very important for us. Okay, of course, if the diameter of the wafer is small, it doesn't matter, a small number of chips can be fabricated. If the diameter of the chip is very high, more number of chips can be accommodated. That's only the important thing. But the diameter, but the thickness of the wafer and the doping concentrations are very, very important for the device to be operated. Okay, so to provide the mechanical strength as well as some other issues will be there. Those are very important. What exactly meaning of this one? Okay, so whenever we are taking the substrate, something like this, okay, better I'll consider it in this way. So I have taken one a chip here. Okay, so it's very difficult to look at the chip at the top level. So top view cannot be understood. How do we fabricate the chip on top view is not possible. Okay, we are not able to understand what is the processing steps, how the layers are formed on a chip. We are not able to see from the top module, from the top view. So it is better to look at the side view. Okay, it is better to look at the side view. Okay, so therefore the side view is most important for us to understand the layer information than that of the top view. Okay, so therefore in that situation, I'm going to consider one particular chip. This is one particular chip. So for example, chip is something like this. Okay, three-dimensional view of the chip is something like this, for example. Okay, so in order to identify, this is a three-dimensional view. Okay, so this is a three-dimensional view. So in this three-dimensional view, it's very difficult to identify. So that means I'm going to introduce the layers, different layers on top of it. Okay, on top of it. So on top of it, again, I'm doing to another thing. So many things we have to do on the top only, but we are not able to visualize this materials on top of it. That's the reason why I have to consider only the side view. Okay, I'm going to consider only the side view. So therefore the side view is something like this. So the side views I'm showing here. So this is what the side view. Okay, so here onwards I can start whatever I'm processing steps are there, those processing steps I'm able to see clearly. Okay, so therefore I'm taking one chip here. So this is the chip here. Okay, so this chip actually consisting of so many materials, so many transistors are there, but in our purpose, the chip contain only one transistor. This chip containing only one transistor, Please remember. So the explanation for everything is the same. So we are going to consider only one transistor on a chip for the explanation purpose, but millions of the transistor will be accommodated on a single chip. Okay, so therefore now whatever the chip that we are taking, so the thickness of this chip, okay, the thickness of the chip as well as the doping concentration are very, very important. Okay, so therefore what is the first step that we have to remember? The doping concentration of the chip or the substrate or a bulk and the thickness of the substrate. So both are very important for us. Why these things we need to consider? Because of it gives the mechanical strength to the device. Okay, as well as the current capability of the device. So preferably we need to consider that the doping the substrate or a bulk a doping concentration thickness are suitable for the mechanical strength. That means whatever the transistor that we fabricated on a substrate, that should withstand the external forces on that particular transistor. Okay, so it has to provide the mechanical strength. That's the reason why the thickness of the substrate is thousands of angstroms that we have to consider. The thickness of the oxide will be thousands of angstroms that we can consider. As we have seen in the previously, most of the cases, instead of saying that meters, we talk about the angstroms actually. But anyway, here is the 0.4 millimeter thickness they have considered. Okay, so therefore, whenever we are fabricating the nMOS transistor, the p-type substrate is important. So the substrate should be p-type. The substrate should be p-type. Very, very important point. Okay, how do we create this p-type substrate? By using the crystal growth technique. Okay, so what are the parameters we have to consider for this substrate? the doping concentration and the thickness is very important. Clear? So is it clear to all of you? What is the first step? The first step to fabricate nMOS transistor is a crystal growth. Crystal growth is nothing but it is used to create a single crystal solid silicon. Okay, and it is used for the purpose of to give the mechanical strength, or it is the house of the transistor. So therefore, on top of that substrate only, we have to create our transistor. So whenever you are creating a transistor on top of a substrate, what are the parameters, what are the characteristics of the substrate should have? The substrate should, the doping concentration of the substrate and the thickness of the substrate, we have to keep in our mind. Clear? Good. Now, the second point is field oxidation. Okay, so somehow we have created this bulk. Okay, so this is the bulk that we have already created. It's a p-type bulk that we have created. Okay. The next point is field oxidation. Okay, so what did the field oxidation will do? Okay, field oxidation will provide, for example, the chip area, this much is the chip area is there. Okay, so this is the chip area. This is what the entire chip, right? So I want to create my transistor only at this part only. I want to create my transistor at this part only. I don't want to use this particular other remaining portions of the chip. I don't want to utilize. So whenever the transistor is placed in a particular place, the transistor is only at this place, remaining portions should not be affected. Okay, so therefore the entire surface of this particular IC will be covered with the dielectric material. It must cover covered with the dielectric material, right? So this dielectric material is formed by silicon dioxide. This is formed by silicon dioxide. That means we have a silicon material, as we know that it is a p-type or n-type, it doesn't matter. Since we have taken the p-type, it is also a silicon material. So how do we form a silicon dioxide? Just we have to place this silicon in oxygen chamber. So just you have to place it in oxygen chamber. Okay, so whenever it is placed in oxygen chamber, so silicon is react with the oxygen and form a silicon dioxide on top of it. So and form a silicon dioxide on top of it. Entire surface is covered with now silicon dioxide. So therefore, it's very difficult to understand what is the top of it. That's the reason why I'm going to consider here is the side view. I can say that. So this is what the silicon dioxide is formed on top of it. Okay, this hatched symbols that no need to use this one. If you want to, if you want to use it, you can use it. Doesn't matter. Just I'm going to consider in this way. It's a p-type substrate. On top of it, I have a oxide. Sorry, yes, silicon dioxide, SiO2. Okay, it's not good to see that one. So I'm going to consider this silicon dioxide on top of it. Are you agree with me? So the side view is very better to look at this one instead of the three-dimensional view, something like that. Okay, so therefore oxidation is the process by which we can create silicon dioxide on top of bare substrate. Clear? So in order to form a silicon dioxide on top of the bare silicon, just we have to keep this silicon material in an oxygen chamber and raise the temperature. Silicon dioxide will form on top of the surface. Okay, so this is very important to note that this is called field oxidation. You have to remember that this is called field oxidation, or it is also called as thick oxide. Thick oxide. So why we need to use the thick oxide or field oxide? In order to protect the unwanted, unused space in the silicon. Okay, unused space in a silicon substrate, we have to use the field oxidation. Okay, now what is the characteristics of this field oxidation? You should remember that the thickness of the field oxide is very, very important. The thickness of the field oxide. So it is generally it is a few thousands of angstroms that we have to consider. So few thousands of angstroms. For example, in meters, so micrometers, it is in millimeters. We observe that this is in millimeters. Okay. So what about the this one? It is in micrometers. So what is the thickness? You can compare the thickness between these two. Okay. So it is actually the millimeters means 10 to the power of minus 3. Okay. So what about 10 to this one? What is the thickness of this one? 10 to the power of minus 6. So that much huge difference is there, the thickness between these two. Okay. So therefore, this much thickness for the substrate is used for the mechanical strength, and this thickness is responsible for to protect the entire bare silicon. Right. So therefore, the second step in order to form a transistor is field oxidation. Okay, fine. Now, once the oxidation is completed, so I want to create my transistor at the top. So at in this particular place, for example, this is what my three-dimensional view of this structure. Okay, so I have formed the entire surface is filled with the entire highlighter. I'll use this one highlighter. So entire surface is filled with the silicon dioxide. Okay, so okay, this is the entire thing is a silicon dioxide. And now what I'm going to do here is that I have to open the window for this one. I have to open the window and I want to make a transistor at this point only. So I want to make a transistor at this point only. So from this point to this point only, I'm going to consider my transistor. So from this one to this portion only, I want to create my transistor. Okay. So for that one, what I have to do, I should remove the silicon dioxide here. Should remove silicon dioxide at this point. So the silicon dioxide is covered in the entire surface, right? I want to selectively remove the silicon dioxide. That's an important one. The selective removal, whenever we are using the selective removal of silicon dioxide, we use the technique called photolithography. What we can call it as photolithography. So by using this photolithography technique, we can remove the silicon dioxide wherever you want to remove, you can remove it. Okay. So, but it involves three important steps. It involves three important steps. One is called photoresist material. Second one is called mask definition. Third one is called UV radiation. Okay. So therefore, we have to remove the, we have to provide the photoresist material. We have to create the mask definition. We have to create the UV radiation. We have to expose that silicon to the UV radiation. So then only it is possible to remove the silicon dioxide effectively. Now the question is that why should I remove the silicon dioxide at that point? Okay, as we know, that first important point is that we want to house the transistor in that particular place only. The second point is that we have to create the gate at that particular portion. Okay, so therefore, in order to create a gate, I have to do this kind of thing. Okay, so therefore, for the gate formation, we have to remove the silicon dioxide over here, over there. Okay, of course, the transistor creation means, transistor formation means, first we have to create the gate only. Okay, so therefore, so that is what we can see. So here, what we have to do, here we have a silicon. Okay, fine, substrate is there. On top of it, we have a field oxide is there. On top of it, we have to create a photoresist material. It's a very important one. It's a photoresist material. What is the meaning of the photoresist material? The photoresist material means it is a polymer actually. Photoresist material is a polymer. Whenever it is exposed to light, its characteristics will changes. Okay, so generally it is a soft material. It is a soft material. Hard material also there, but anyway, consider this is a soft photoresist material. Photoresist material is a soft material. So what I have to do, I have to remove the silicon dioxide at this portion, right? I want to remove the silicon dioxide at this portion. So if you want to remove the silicon dioxide at this portion, that means I should remove the photoresist material on top of it. Okay, so because I cannot place the photoresist material only one place. Okay, because it is a diffusion process. It is a deposition process. Deposition means by using the gas inlets, we are providing the gas inlets on top of it. Therefore, it will cover the entire region. So it is not possible to place only one particular portion. It's not possible. So it must be cover the entire surface. So if it is the entire surface, but photoresist material only one place is not sufficient to remove. So that's the reason why what I had to do. Okay, let it be cover the photoresist material on the entire surface. Now I can remove only certain portion so that field oxidation can be removed effectively. Okay, so therefore what I have to do here is that, so I have to remove the silicon dioxide, sorry, photoresist material at this place. For that one, what I have to do is that I have to create a mask here. I have to create a mask. So mask is nothing but one glass plate, and we have to etch some patterns. So we have to create some patterns on it where exactly we want to remove the photoresist material. Okay, I want to remove the photoresist material at this portion, means I have to use the dark coated material for this glass plate. Okay, so then what is happening here is that whenever the light is exposed here, so these portions, what the exposed portions of the photoresist material will become hard, will become hard because of the light exposure. So here also this particular portion of the photoresist material becomes very hard. It's not possible to remove at all. Okay, so but whatever the at middle point, I can say that these portions are not at all transparent to the light. Therefore, it always becomes soft only. Soft only. It becomes only soft only. Right? So therefore, what I can do is that, so this is how the second step is mask definition. So the first step is photoresist material deposition. Okay, then the third one is actually UV radiation. Whenever you are using the UV radiation, the material, photoresist material, sometimes it is hot, sometimes it is soft, depending upon the light exposure. So here we have considered that initially soft photoresist material we have taken. Whenever the light is exposed, that portion of the photoresist material becomes very hard. Okay, it's not possible to remove. Now, the soft photoresist material I should remove, right? For that one, what I have to do is that I use sulfuric acid, this H2SO4. So the sulfuric acid is used to remove the soft photoresist material. Of course, the same diagram only I have used here for the clarity purpose. Okay, so therefore this is what we can say that. Right? So therefore, so this portion of the photoresist material I should remove now. So how do we remove this one? Just use the hydrofluoric acid. So sulfuric acid we have to use. So with the help of that one, we can remove that portion. Okay, so therefore we have removed this portion. See here, you can remove this portion of the photoresist material. Are you agree with me? So this portion of the photoresist material is removed now. Okay. Now, so here the silicon dioxide is available here. Okay, sorry, I'm sorry. So this is actually field oxidation is available. Yeah, it is the silicon dioxide now. So if you want to remove the silicon dioxide, okay, what I have to do is that I should use the hydrofluoric acid. So dip this one into the hydrofluoric acid. Okay, so whenever using the hydrofluoric acid, only that portion of that, whatever the covered area of the photoresist material under the silicon dioxide, sorry, above the silicon dioxide, it's not at all affected. It remains the same. So okay, so that the given sulfuric acid can remove only the portions of the exposed silicon dioxide. Clear? So the silicon dioxide can be removed by using the sulfuric acid. So other portions of the silicon dioxide is not at all removed. Why? Because on top of it, we have a photoresist material. So the photoresist material will absorb the sulfuric hydrofluoric acid to remove. But whenever the photoresist material is not there, that portion is exposed to the hydrofluoric acid, and that hydrofluoric acid can remove the required silicon dioxide. Okay. Now, once the purpose is completed, and we can remove the photoresist material as it is. Again, we have to provide some light here so that it becomes very hard. So now it is a hard material now. Okay, it is a very hard material. So now it must be soft by using some mechanism. Okay, so we have to define a mask and UV radiation again, and this becomes very soft. It will be converted into very soft, and we can remove that portion by using sulfuric acid, some other things. Okay. So anyway, our point is that we want to remove the silicon dioxide select in a given portion. That is how we have removed the silicon dioxide here at this place. Okay, of course, we are writing a very sharp edges here, but it's not reality. It's not a sharp edges. Some kind of edges also will be affected, and something like this it will show. So this is called opening the window. What we can call it as, it's opening the window to house our transistor at that particular place. So what we have done so far, crystal growth we have done. That means the substrate is formatted, substrate is formed. The second point is that field oxidation. The third point is that open the window for gate, open the window for transistor. Okay, that's what we have done so far. Okay, now the next point is gate oxidation. So very important one is gate oxidation, or we can call it as thin oxide. Thin. Earlier field oxidation is called thick oxide. Now it is called very thin oxide. Okay, so it's what is the difference, the thickness difference between the field oxide and gate oxide? So we can say that the gate oxide should be 1/10 of the field oxide. 1/10 of the field oxide. For example, you consider the thickness of the silicon dioxide is field oxide is 1 micron, for example. So, but now the gate oxide should be 0.1 microns. It should be 0.1 microns. Okay, 1/10 of the oxide we have to consider. Clear? And another important point is that very pure oxide that we have to consider. Okay, so because of the people were not able to realize these two things, even though we know the theory behind the MOSFETs well before the bipolar junction transistor. For example, the theory of the MOSFETs are initiated at 1925 to 1930, around in this one. But MOSFETs, bipolar junction transistors came into existence in the year 1947 onwards. Okay, so but MOSFET theory is known very well defined in previous days when compared to the 1947. BJTs came after 1947. But the MOSFETs are not able to realize why it is so. Because of these two reasons, they were not able to realize that much the small thickness field oxide, and the very important thing is that purity of the oxide they were not achieved. So what do you mean by the purity of oxide? Purity of the oxide, an oxide responsibility is that there is no transportation of the carriers. It should be strictly, it's an insulator, for example. Okay, but if some mobile carriers are there in the oxide, means it becomes impure oxide. That means the responsibility of the insulator is not performing there, because the free carriers are available in the oxide. Okay, so therefore the pure oxide is very important for us. So in order to construct a transistor operation properly, the pure oxide is very important. Okay, so therefore what we can do is that we have to deposit the photoresist, we have to deposit the gate oxide on top of the field oxide. Okay, so how do we deposit this one? It is similar process of the gate oxidation only, but care must be taken, the pure material that we have to form there. Okay, so therefore what we have done here, we have a silicon, we have an oxide we have created. It's a pure gate oxide. Thickness is very small thickness, that a few fraction of angstroms we can call it as. Right, so that is very important. So there should not be any kind of mobile carriers in the oxide. Fine. Now, so once the gate oxide is realized, the next step is realization of the gate. Realization of the gate. Normally we use normally what we have done here is that we have created a gate oxide. On top of it, we have to create a metal here. Metal oxide semiconductor we have to create. Right. So, but instead of using the metal here, we use the polysilicon gate technology. It is a self-aligned technology. Polysilicon. Polysilicon technology I'm using. What do you mean by a polysilicon technology? Just the gate must be realized with polysilicon. As simple as that. Okay, so therefore there is some issues with the metal when it is exposed to the high temperatures. Okay, so that's the reason why we have to use the polysilicon gate technology. Okay, there is some issues are there with that one with the metal. So that's the reason why we use the polysilicon technology. So how do we realize a polysilicon on top of it? So by using the CVD technique, chemical vapor deposition technique. Deposition. Deposition means we on top of it we have to create it. Okay. So this is what we have to create a polysilicon on top of it. Okay. It is also few 1 micron to 2 micron thickness will be there. Okay. Polysilicon layer. Right. Now, so we have realized the gate. Okay, so therefore we have realized the substrate, we have realized the oxide, we have realized the polysilicon as a gate. Now our responsibility is that we have to create source, we have to create a drain, right? So how do we create the source and drain? Then we have to do that by using again what the source and drains are removed. Actually what we have to do, so only the gate is available at this portion only, please remember here. So gate and oxide and everything should be there at this point only, no other places is required. So we have a polysilicon, we have an oxide, we have a semiconductor. So only this portion is sufficient for us, right? Only this portion is sufficient. So these portions we are used for the purpose of the source, this is for the drain. So in this place you can observe carefully, these things are not necessary to provide. Not required. This portion is also not required. So the metal, the polysilicon and oxide and semiconductor portion is required. That is a very heart of the structure. Okay, MOSFET structure. So other portions of the polysilicon, other portions of the gate oxide is not required. Okay, that related portion must be removed. Okay, therefore that means that I have to remove the polysilicon in unwanted portions. For example, here the polysilicon is not required. So from this point to this point, polysilicon is not required. So again, from this point to this point, polysilicon is not required, right? So we have to remove these polysilicons. So in order to remove this polysilicon, etching process we have to use. By using the etching process, we can remove the polysilicon effectively. Okay, so therefore by using the etching process, we can remove poly. Okay, instead of polysilicon, we also call it as poly also. So the gate oxide, unwanted gate oxide can be removed by using the HF solution, hydrofluoric solution. So because under the polysilicon, we have a gate oxide that cannot be disturbed because the polysilicon is covering the gate oxide under that. Okay, remaining portions of the gate oxide only can be removed by using some small mechanisms, because if the thickness is very small, so no need to worry about it. It can be removed very easily. Okay, that's good. Now, so in order to do this one, this is the same process we have to use. Go for the polysilicon, go for the selective removal of the materials by using the photolithography process. Somehow we have removed the portions at this point. You can observe carefully. So somewhat we can remove the portions of the silicon dioxide. Photolithography properties, resist material is also there. That resist material is also can be removed somehow. Okay, by using the patterning differently. Now this is what we can see here. So the conventionally, this is what the substrate. Okay, so we have a field oxide, we have a field oxide, we have opened the window for the source, we have opened the window for the drain. Okay, so in reality it look like something like this. Of course, not necessary to remove the oxide at this place. Gate oxide remove parvalid. Okay, or maybe some portions of this one is also can be there. So theoretically, we can say that just we have removed, but practically something will be there, gate oxide. It doesn't matter. Okay, so some portions of the source material, some portion of the drain is required. Small portions of the source and drains are required. Okay, that's the reason why they have shown here is the SI water field oxide, field oxide. It is a gate oxide, gate oxide. Okay, so only these portions of these things are must be removed. Okay, after some time we can also remove this one. So for I have done that one. So that's the reason why I'm using this is the one. Okay, so that's the reason why without any difficulty in it, just I have opened the window for this one. I have opened the window here for the source. I have opened the window for the drain. Okay, now, so by using the technique called just within 1 minute, I'll come within 2 minutes, I'll complete it. So by using the source, by using the diffusion technique, ion implantation technique, by using the ion implantation techniques, we can provide a source and drain. So both are n-type material, n plus diffusion technique that we have to. Diffusion is the technique we have to use. So by using the n plus dopants, we can diffuse inside the substrate. Okay, diffuse means penetrate into another material. Deposition means on top of it, it will be covered. Okay, so what is the technique here? We use the ion implantation technique. Okay, so by using ion implantation technique, source and drains can be realized. Okay, so therefore the transistor is formed. Okay, we have created the p-type substrate, we have created the gate oxide, we have created the polysilicon, we have created the source, we have created the drain. What is the last step? So we have to provide some terminals over here. Okay, so one terminals that we have to create for the external connection. Okay, that means that providing the external connections to the transistor is called metallization. Is called metallization. So therefore the metallization is the technique that we have to use. The same diagram only after entire thing is diffused here, it is better to cover the entire portion with the field oxide. So cover the entire region with the field oxide again. Okay, so whenever one process is completed, it's better to use the field oxide. So that's what I have written here. It's usual practice, we have to create the field oxide. Please remember that it is a field oxide to cover the entire region. So when and where we want to open the window, we can do that one also. So remove that portion also. So therefore the final one is metallization. So in the metallization means the same thing we have to follow. Just to open the window for this particular portion. Okay, open the window at this portion, open the window at this portion. The selective removal of the silicon dioxide in the given portions use the technique called photolithography, right? So by using the photolithography process, we can remove this one and we can deposit the aluminum material. We can deposit the aluminum material. Therefore, just this is what the aluminum, aluminum material that we have to deposit here. But aluminum is not necessary, which means that the source is shorted to the drain is shorted to the gate. So this is not should not be there. Only certain portions of the material is required. So that means that only this portion of the metal is required, only this portion of the metal is required, only this portion of the metal is required. In that case, again, photolithography process we have to use to remove the unwanted portions of the metal. Okay, therefore, this is how it look like. So we have a source here, we have a gate here, we have a drain here. Okay, so here also that will be shown effectively in this one. So this is the metal, this is also metal, this is also metal. So this metal is meant for the source, this metal is meant for drain, this metal is meant for the gate. Okay, so this is how we can fabricate a nMOS transistor. Similar concept is applicable for the PMOS also. MOSFET also, but only thing is that, so instead of this is a what we have to do is that this must be n-type material. If this is the same gate oxide, polysilicon is also same, but this must be p plus diffusions are required, p plus ion implantation is required, and metallization is also the same. Metallization is same. Metallization is same. So this is what to take it as a homework for the PMOS substrate, the PMOS transistor fabrication. And we will see the tomorrow, how do we fabricate CMOS fabrication? How do we, what are the steps involved in the CMOS fabrication? Okay, we stop here today and we will see the remaining things in the next class. Okay, thank you.